Welcome to our presentation of a visual scenario-based environmental analysis approach to the model-based management of water extremes in urban regions. Nowadays, the climate crisis has become more and more apparent in everyday life. An increasing number of short and long-term water extreme events threatens lives in urban regions more frequently. Throughout Europe, the number of flood events has increased tremendously. The number of people affected and the total economic loss has increased significantly. The prolonged drought seasons and increased water shortages may create even higher risks for the inhabitants. The observation and analysis of the water cycle and the estimation of future risks in terms of preventing possible upcoming disasters has become more crucial. The prospective future risk analysis and possible disaster estimation in urban regions due to water extremes requires a collaborative involvement of broad working groups with a similar focus. From this motivation, we present a set of such studies including observation dataset collection, analysis of the relationship between datasets, creating numerical simulations based on such data, and the development of a model-based coupled approach. We focus on the visualization of the various environmental compartments. The goal of the study is to provide a scenario-based 3D visual environmental application that enables domain scientists to explore the relevant data, reach out to stakeholders and interesting public groups, predicting the risk of the future casualties and damages as well as precautions to prevent such disasters. In our case study, the examined region Dresden, the capital city of Free State of Saxony in Germany, with a population of more than 560,000 inhabitants, is the second largest city located in the Elbe basin. It is located within a narrow valley in a relatively mountainous terrain. It is one of the cities having the largest flood risks in the Elbe catchment, since the Elbe River starts to overflow its increased volumetric mass around the region due to heavy precipitation occurring upstream and in its regional catchment. The geographic 3D representation of the topographic frame of reference has been generated from the digital elevation model in 1 meter resolution of the region. A vector dataset representing the boundary of the city of Dresden obtained from the open-access geographic environmental data libraries of the state of Saxony. After tessellating the georeference boundary, we applied the DEM of the region of interest to add elevation information using the OpenGeoSys Data Explorer, and thus received a highly detailed surface mesh consisting of over 1.2 million triangles with a 30 meter resolution. The raster aerial imagery of a rectangular area covering the area of the city in 25 meter resolution has been projected into the same coordinate reference system, used as a high resolution texture to the surface mesh. We utilized Unity 3D graphics and game engine for building a virtual geographic environment for the environmental impact analysis. We have built a framework to generate a virtual geographic environment for the visual demonstration of environmental data in previous studies. The framework proposes a wide range of toolkits to import and represent a variety of environmental datasets from various sources, to define visual characteristics and visibility properties of improved datasets, to create a storyline by some presentation-specific features, and to interact with the properties and runtime parameters of the data. In this study, the framework has been enhanced and diversified to meet the requirements of both visualization of urban infrastructure and hydrological datasets. The capacity of the data import and integration module has been upgraded to support a variety of data types, such as high-resolution 3D urban models. The surface and line mesh renders have been improved to accurately visualize the water body accumulation, and sewage runoff simulations. We made some improvements in the storyline configuration manager, the viewpoint interpolator, and the visual settings manager of the data presentation layer, and we made some enhancements of time series data animation interfaces, lighting settings, and vertex shader procedures for the accurate data representation during the runtime. As a digital city model, we have incorporated CityGML open access model data of the City of Dresden, which is subdivided into 2 by 2 km square blocks. The level of detail 2 dataset is consisting of a total of 11 predefined separate building types. A script-based data importer has been employed to create triangulated polygons from the corresponding defined locations of each infrastructure element. Predefined semantic entities have been then used to create different materials so that the wall, roof, and the ground sections of the buildings could be visualized in different colors. In total, 26 blocks of most populated areas of urban infrastructure data of Dresden have been integrated into the VGE, consisting of over 2.3 million triangles. Acquisition of reliable historic groundwater level observation data for the analysis of ground and surface water relationship is substantial. The database of the Free State of Saxony provides the daily groundwater measurements of all the observation sites until 2019 with varying measurement frequencies. We have created a shapefile out of this database as georeferenced location markers to display them within QGIS software. We have then cropped this data regionally around the rectangular bounding box around the City of Dresden. We have applied a query-based database filter to gather all the monthly measurements between 2015 and 2018 to analyze the seasonal fluctuations with a 4-year time frame. To construct a special 3D animation of the data, we first have sliced the filtered data regarding their measurement dates and created 48 sets of groundwater measurement data of all the stations. Then we specially interpolated using the kriging method to create 2D raster data of interpolated groundwater head levels for every time step. These extracted raster data have then been used to map 3D surfaces out of the interpolated raster files. That way, we produced 48 surfaces of the groundwater location for the 48 monthly points in time. We used depth attribute for texturing the resulting surface with a depth and base color map, which allows the inference of 2 different attributes at the same time. Hydrologic and hydraulic models require various additional input data sources such as soil infiltration, evapotranspiration, or surface roughness. Therefore, publicly available land use and biotype data was processed. The land use data consisting of multiple categories of buildings, water bodies, urban infrastructures, and vegetation was clipped, merged, and dissolved with the transport infrastructure. Then multiple redundant land use classes were further aggregated, leading to 15 distinct types. Finally, the vector data was rasterized using the provided color scheme and stored as a geotiff for later texturing purposes. Being one of the severely affected districts in previous floods, Lockwitzbach district in southeastern Dresden is a well-suited study region for water management. The topographic virtual surface of the Lockwitzbach area is also generated by the same surface generation method at 20-meter resolution and integrated into VGE as a modeling and simulation base. The initial stage of the coupled hydraulic simulations is a surface runoff model driven by heavy precipitation events. A computational triangle mesh was created using basement software tools. The mesh consists of approximately 3 million cells for a total of roughly 35 kilometers square. The base model was refined with additional per cell data such as surface roughness and precipitation runoff transformations, taking infiltration and transpiration into account. The created surface runoff model uses Euler-2 design storms as a boundary condition for precipitation input, which were generated using Lars stochastic weather generator. The design storm projections were conducted for 2 feature periods: near future from 2014 to 2060 and far future from 2081 to 2100. After running a heavy precipitation simulation, results include water depth, flow velocity, and specific discharge per computational cell for an adjustable time step. For the sewer system runoff simulation, a stormwater management model has been developed with the tool GISTO SVMM5 using sewer system network data in combination with land use data, a digital elevation model, and hydrological data derived from the digital elevation model. The model has been coupled to a groundwater model and a surface flow model using Python and the SVMM API package. For groundwater flow demonstration in the Lochwitzbach area, we used a simplified quasi-steady-state model in OpenGeosis. The groundwater was driven by boundary conditions in the west and the river Elbe in the east, which are based on measured historical data. A part of the sewer network was included into the model in order to mimic infiltration and exfiltration scenarios depending on groundwater level fluctuations. The numerical simulation shows the temporal evolution of the groundwater surface and velocity distribution in the catchment during the simulated time period of almost 4 years. The overall visualization pipeline starts with georeferencing the data into the predefined coordinate reference system. For this particular study, all the datasets are reprojected to UTM Zone 32N reference system in QGIS application. Afterwards, they are converted into 3D data with the application of a significant attribute, mostly the elevation of the data, in OGS Data Explorer. The mentioned 3D data can either be a surface mesh or a 3D representation of vector data. Line strip data type is used for representation of the rivers and streams, while the measurement stations are defined as point data. All of the georeferenced datasets are exported into GLTF file format so that the proposed Unity presentation framework can import and properly transform all the datasets into the VGE. The storyline represents an intuitive way of presenting the integrated static data and dynamic simulation results. A storyline requires the definition of a sequence of points of interest and the suitable presentation of datasets and simulations at each of these points. The visual properties of the data are namely the type of visual representation of the vector data or raster data, the opacity and the apparency in the scene at a determined time period, the ability of controlling the elevation and vertical position, the timeline control of the time series simulations. And the viewpoint configuration function includes building descriptions and positioning of virtual cameras rendering the particular region of interest, the definition of the transition track of the virtual cameras coherent with the narration of the story, and the alteration of the visual properties of the focus datasets according to the active viewpoint's field of view. Therefore, visual data characteristics and transition during scenario-specific viewpoints are adjusted beforehand. Redefinition of these properties is optionally possible during runtime via user interface interaction modules. Thus, perpetual scenario flow has been enabled to demonstrate all the coupled datasets. In the study, we proposed a visual scenario-based environmental analysis method utilizing a VGE for the model-based management of water extremes in urban regions based on a case study for the City of Dresden. Some distinctive features of the proposed application include the interactive exploration of the virtual urban region, the integration of numerical models and environmental simulation scenarios for the visualization and analysis of the environmental impact, the integration of multiple environmental compartments within a geographic context, and the control of the synchronized animation of multiple 3D time series datasets with varying spatial and temporal resolution. We have presented a methodical approach and tools to generate, couple, and visualize hydrological and hydrodynamical models based on a digital urban model to improve communication and increase risk awareness. We have thus created a platform for the collaboration between researchers, stakeholders, and interested public groups from the domains of water management and distribution for the assessment and prevention of future risks. This work is a part of the Sächsische Aufbaubank project, WET Urban, which is co-financed on the budget passed by the Saxon State Parliament. Many thanks for all my co-authors who supply, create, and process all the datasets and numerical models visualized in this study. I hope you enjoyed the presentation and looking forward to answer your questions. Thank you very much.